So this lesson is kind of doing all kinds of different polynomial problems. I'm going to work a couple of them. Then I want you guys to try the last three or so on your own. So they're just kind of real-world applications for where we can use polynomials in different situations. The box problem here is one of the ones you see the most often. An open box is to be made of a piece of cardboard with original dimensions of 6 by 8. So let's start by drawing a picture for what's going on. So we have laid flat a piece of cardboard that is 6 inches by 8 inches. Okay, there we go. It says we're going to be cutting equal squares from all the corners and turning up the sides. So in every corner, we're cutting a square. So we're going to continue cutting corners. Now, all I know is that they're all equal squares. So do I know what the length of the sides are? I don't, but anytime I have an unknown, we can use x. And because they're squares, we know that all of them would have a value of x from what I'm cutting out of the corner. So A, draw a picture that represents the piece of cardboard by cutting of equal squares. So we've done that here on A. B, write a formula that expresses the volume of the box in terms of x, the amount that was cut from each corner. So this is the part that's going to be hard for me to draw. So let me show you someone who can draw and their representation, and we'll kind of talk about how they got that. Okay, so just look here very quickly. Think about it. If the side length here was originally 6 inches and I cut x off from here and x off from here, then what is this little piece? This is all that's left. Well, the whole thing used to be 6, but I lost x and I lost another x, so that makes that side length become 6 minus 2x. And if you can think about visually cutting these corners out, that gives you a way you can fold the box up to make it be in this position. All right, so that's where they get this side length of 6 minus 2x, because you're losing both of those x's. And then same here with the 8 minus 2x. This whole side length used to be 8. If I cut the corners, now it's 8 minus 2x. And then again, if I'm folding it here and standing this part up, then the height of the box would be that x value. Whatever this part that's foldable, that'll be right here. This gives me the x, and then this part's going to get folded up to here, and so on and so on. So hopefully you can visually see that. So B, write a formula that expresses the volume of the box in terms of x. Well, you can see to find volume of a rectangular prism, we just multiply length times width times height. And that's what they've done here. Okay, C, find an interval for which x would make sense to the problem. Well, if I cut squares that are side length 0, that doesn't make sense. So it has to be a number bigger than 0, right? But then what's the biggest value that x could be? Again, if you think about it here, if I made x 3, okay, well then this would be a 3-inch loss and a 3-inch loss, which means this side length would be 0 now. Well, I can't have a 0 side length or I wouldn't have a box. So the x value has to be smaller than 3. So bigger than 0, smaller than 3. So 0 is less than, x is less than 3. So again, here's the interval, and this is an interval notation, or here's another way you can write it. And then D, find the maximum point and explain what it means to the problem. So again, if you think about our formula that we wrote here, volume is equal to, and then I've got three factors here. So graphically, the y value is the volume, and the x value is the box cut length. And so all we have to do is put this in our graphing calculator. So you can see here, they have typed in y equals x, that's the height, times 8 minus 2x, the length, 6 minus 2x, the width. And you can see here, here's an x value of 0, so it has to be bigger than 0, and it has to be less than 3. So again, graphically, we're seeing how that makes sense. And if we're looking for the maximum point, let's see, it kind of looks like, if I zoom into this part, it kind of looks like a parabola. So we had to restrict the domain. We only care about x's between 0 and 3. So when they're asking for the max point, I'm looking for the highest there. So in our calculator, we can use, I don't have one in front of me, second trace, let's calculate. And then there should be a place that you can select maximum value. And then you're just going to put up your goalpost. So say you want to find the max value between, and you could just type in x being 0 and x being 3, right as my goalpost. And what's the highest y value the graph takes on between there? Because those are the only x's that make sense. And you can see here from the graph, they've got 1.1314853 is the x value, and 24.258 is the y value. So what that means is the maximum volume that the box can be is 24.258 cubic inches. And in order to get that max volume, I need to cut a side length of 1.131 inch squares from each corner. Okay, 2, the height, y, in feet of a baseball is given by, there's the parabola, y equals negative 16t squared plus 64t plus 3, where t is in seconds. Give the window that allows you to view the function. So what you want to do is type this in your graphing calculator, and then figure out what are the values that make sense for x, or in this case, the x value is represented by t. So t is time. So again, I don't have my graphing calculator, so I'm going to look at what they graphed here. If y is the height of a baseball, does it make sense to have a negative height of the baseball? It doesn't. So I'm only looking for the places where the y value is positive up here, and that happens between 0 and a little after 4. So they chose the window to be time being between -1 and 5. And that's fine, but it doesn't have to be that. It could be anything that allows you to see all of this curve, like this. And then what about the y values on the window? So we would want to find the max y value. So the lowest y value that makes sense is 0. And then the highest y value, you just have to keep trying until you could find the top of the parabola. And so it ends up the top is at 67. So anything above that would be good for the upper part of your window. B, how high is the ball at the beginning of its trajectory? So as soon as it's hit, what's its height? So really what I'm wanting to know is when t is 0, when time is 0. So think about plugging 0 here and here. What is your y value? It's 3. So it's already 3 feet off the ground, which makes sense because if the baseball was 0 feet off the ground, he'd be hitting it like a golf ball, right? So it makes sense it has to be up some. That's why the y-intercept's not 0. It's 3. And then C says, how high is the ball when it's at its maximum? So again, on your graphing calculator, look up second trace, and then look at that maximum between the goalpost. It turns out it's here, and it spits out at me 1.999998. is how many seconds it's been in the air. So we can just estimate this to be 2 seconds. So 2 seconds into its flight, it has a height of 67 feet. So that's its highest point. So what I want you to do, I want you to try the next 3. The third one is another box problem, very similar to the one we just did. So 3 is a box problem, kind of like 1. 4 is similar to 2. And it's also got some parts of 1 in it as well, where we're talking about area, maximizing area, where 1 was volume. Right, so it's similar there. And then 5 is kind of different. It's a population problem, but it's still the same idea. So try those 3, and I'm going to put the answers up here. So after looking at the answers, it's going to be hard to put them on the iPad. So what we're going to do is I'm going to upload a PDF with the answers to 3, 4, and 5 for you to check your work once you're finished.